Hey, this is Mr. Boggs, and today we're going to talk about the science of sound waves. So sound waves, they differ from electromagnetic waves in that they need a medium to transfer through or to travel through. And so in other words, light that comes from the sun travels very quickly through empty space and reaches the earth, but those sound waves from the sun, they simply can't travel through the vacuum of space. And so to emphasize that, I want to show you what the last scene of Star Wars would look like if it actually followed the rules of science. And so let's take a look at that real quick. And so why can't we hear the Death Star explode? It's just simply that the sound doesn't have anything to travel through. And so that's probably one of the misconceptions that people have about sound, is that it can travel through outer space, and that's probably because we watched a lot of movies. So a couple things that we need to know about sound waves. First, it's a mechanical wave. And so it needs some type of matter to travel through. If it has nothing, no matter to travel through, then it simply won't go anywhere. Another thing is that it's a longitudinal wave, and so, or a compressional wave. There are transverse waves where the waves, the matter that it's traveling through is moving up and down, and the energy is traveling perpendicular to that. And so that would be like if you had a rope and you sent a wave down that rope. That would be a transverse wave. The matter is moving up and down, but the energy is going in perpendicular to that in a different direction. Longitudinal waves, those are like a speaker. So if a speaker's oscillating in and out, it's creating a compressional wave, and so the matter is moving in the same direction as the wave. And so what would that look like if we looked at this 3D image here? That's what a compressional wave would look like if it's coming out. So if you're listening to my voice right now, my vocal cords are vibrating in the air, and it's vibrating that air and sending it to the speaker, and the microphone is picking up those vibrations. And so what would it look like if you could see my voice? Sorry. So what would it look like if you could see my voice? It would be this three-dimensional shape moving out, and so that energy is spreading out over a larger distance. How does temperature and density affect the speed of sound? And so if we look at this chart here, if we looked at temperature first, how does temperature affect it? So if we have air at 0 degrees Celsius, it travels about 330 meters per second. If we increase that temperature of air to 20 degrees Celsius, it's going to speed up that sound wave, and so it can travel about 340 meters every second. And so the same thing with water. If we go from 0 degrees Celsius to 20 degrees Celsius, it speeds up that sound wave. How does density affect the speed of sound? Well, if we compared air to water, which one's going to be more dense? The water. And so if we look at the speeds, air at 20 degrees Celsius is 340 meters per second. Water is going to be 1,500 meters per second. So the more dense an object is, the faster the sound will travel. And if you get even more dense, if we compared that to steel is about 5,800 meters every second. And so why is that? If we think about those individual molecules, if we compared still to air, those molecules are going to be really compact and close together. So the energy traveling from one molecule to the next, it's going to be a lot easier for it to go that distance. But if we talk about air, those molecules are spread out and moving around. It's going to take a longer distance to transfer that energy to the other molecules. So it's going to go slower than it would in steel. Same thing with temperature, why that works. Those molecules, if you increase the temperature of water, what happens to the molecules? They start to move. They might be moving like this, and if you increase the temperature, they move a lot faster. And so those molecules can transfer that energy quicker. So it can move faster through warmer water than it would colder water. Frequency and pitch. So in music, we talk about pitch. So if we have a high pitch, we're really talking about frequency. And so remember, frequency is how frequent those waves are passing a fixed point. And so it's how many waves are going past there. And so if you increase frequency, then you increase pitch. And so you can have a low pitch sound, like a bass sound, and then you can have really high pitch sounds. And that just has to do with the frequency. Amplitude and loudness. So amplitude is how much energy you have in a wave. And so if you look at a wave and you have an amplitude with really high energy or a really high amplitude, it's going to be a really loud sound. And so you may have an amplitude that looks like this or a wave that looks like this. And if you turn down the volume, you turn down how loud it is, your amplitude would go down. And so does amplitude affect frequency? No, it doesn't affect frequency. So you can have really big waves and still have them moving, or still have the same amount of waves that pass a given point. So how do we perceive sound, and how does the ear work? Whenever we perceive sound, those vibrations are entering our auditory canal, and then they're going to vibrate the eardrum here. And so the vibrate in turn vibrates these little bones in our ear, and they're attached to the cochlea. And the cochlea is what does all the processing of sound. So inside the cochlea, if you opened it up, you would find that it's full of fluid, and it also has little hair cells that line the inside of the cochlea. And so when those hair cells start to vibrate, then they're sending signals to our brain that we interpret as sound. And so if we actually, you can see that the cochlea kind of looks like a snail shape. So it's this tube that's wrapped around in a spiral shape here, and it gets more narrow as you get toward the center. And so if you unwound that cochlea, it would look something like this. So you have an area where there's a really big tube, and then it gets more narrow. And so on the big side, you're picking up those high frequencies, so the 20,000 hertz. And then on the low side, on the smaller side, you're picking up the lower frequencies. So we have this range. Because our cochlea is a certain size, we have a range in which we can hear different frequencies. And so with pitch, or our frequency, literature tells us that we can hear about 20 hertz to about 20,000 kilohertz. And so that's for the human range. For loudness, or our amplitude, we can hear about 0 decibels to about 130 decibels. And you probably can't hear more than that, but it's going to be damaging to your ear. In fact, if you get about 125 decibels, I believe it says, then that's going to be painful. That's going to be the pain threshold, and it's going to hurt your ears to hear that, and it can damage your ears. And over time, as you get older, you're going to be exposed to loud noises, regardless, and so that's going to damage some of those hairs in the cochlea, and so they can either get destroyed or damaged, and that's going to narrow that range of sound that you can actually hear, or frequencies. In fact, if we kind of played around with that, which I have a tone generator on my phone here, and so I can generate different frequencies. And so if I played it right now, this would be that sound right there. Let me turn it up just a little bit. That would be equivalent to a C note, so 262 hertz. If we doubled that, it would sound like this. So if we went to, let's see, about 500, and what would we double that? 523. would sound like that. So that's a high C note. And so if we went toward the top, we increased it, it would sound like this. And so let's go into the thousands. It gets really annoying. And if we get upward toward the top of our range, so I'm at 10,000 hertz, 11,000, 12,000, 13, it's kind of painful. About 16,000 hertz, I can't hear that anymore. And whenever I was in class, I don't know if you guys can hear that over the speaker or not. If you can, it's really annoying right now. But I can't hear that anymore because some of those hairs in the cochlea have been damaged. Where younger people, they still have those hairs, the hair cells, and they can hear those sounds. So I'll increase it to about 18,000. I still can't hear anything. 19. There's 20,000 hertz. And so if you compare that, if you want to do that with like your parents or your grandparents even, compare your hearing to their hearing, and you'll see the difference with that. So that's the cochlea and how the cochlea works and how you perceive sound. Resonance. So we talked about resonance a little bit. What is resonance exactly? So resonance is when a material or an object can absorb energy at its natural frequency. And so materials and objects, they have a natural frequency that they make, or they create noise. And so if we had tuning forks here, you can see that they're different size and they're going to have different frequencies. And so if we actually hit those together and we stopped one, I don't know if you can hear the sound here. So that one has a different frequency of that one. Then that one, it's going to have a different sound. But so that's what resonance is. It's the ability of objects to absorb energy using its natural frequency. And so if you've ever seen wine glasses or heard of people breaking those wine glasses using their voice, what they're doing is matching that frequency, and if you increase the amplitude enough, how loud it is, then you're able to shatter that glass. And so this is a slow motion of what a wine glass is actually doing when it's vibrating. And so if the natural frequency of that wine glass is 340 hertz, then it's actually vibrating in and out 340 times per second, every second. And so if you didn't have it slowed down like this, you wouldn't even be able to see it vibrating in your hand. But that's also why in the lab, whenever we blew in the test tubes, or if you blow in a bottle and you create that really good sound that comes out, you're vibrating that air at its natural frequency, and it's resonating in there, and it amplifies the sound in there. Same thing with instruments like guitars. They have that hollow inside. That's a resonator, or a resonant tube, and it is amplifying that sound so you can hear it better. Other uses for sound are things like sonar. These are just different names that we give, but basically it's the same process. Echolocation and ultrasound. So if you're using sonar to find things underneath the water, then we're sending out these waves, and if we know the speed of sound in water, around 1,500 meters per second, then we can time how long it takes that wave to go through the water and hit an object and be reflected back. And so we can actually create images using different depths, and so that's what ultrasound does. So the picture of the baby down here, the baby's not actually yellow, it just gives it color because ultrasound can't pick up color. But the depth of his arm right here would be different than the depth of his arm closer to the ultrasound tool there. And so it can create these images, and you can see what's inside of different things without actually having to see them. So it's using sound. Same thing with bats or any animal. They use echolocation. They're sending out those waves, and when they bounce back, they can know how far away they are. And so that's sound.